Definition. The triple integral. The triple integral of some function f over d, this is what we're defining here, is given as now we have triple integral. Here is our function with respect to 3 variables. And the differential is not going to be just a single x anymore. It's not going to be even an area patch. So we're doing 3 dimensions. So we need a volume differential, dV. And this is given as a very similar limit construction as we've been doing every single time. So delta goes to 0, delta sum of Rk is 1 in a function where we have each of the variables we're choosing some x sub k star, y sub k star, and z sub k star in your box petition. And then we take these little cubes of changes of delta b. Okay, so when we were talking about the bathroom tiles or DAs, you guys remember that?
Yeah.
So now I want you to imagine, oh, actually, this is basically Minecraft. Okay, so when you're constructing something, each individual dirt block that you're placing, if you're trying to make a little like a mound or a hill or something, each of those blocks is not perfect. So nothing in Minecraft is completely smooth, right? So even if you look at like a slope or a hill, it's blocky as you go up. And so that's kind of what we're doing. We're taking these delta V. So each one of these changes of the volume sub K is like an individual block on like a Minecraft mountain or whatever. And so this summation would be taking the volume of every single one of those blocks that makes your mountain formation. And then the delta going to 0 is basically saying, imagine you can make those, the blockiness infinitely precise because it makes it, yes. These are asterisks. It's just a way we denote you've chosen some coordinate inside of the volume box. Very Riemannian. You don't need to worry too much about that. If you want to see the visual kind of intuitive proof in the textbook, it's there. But yeah, so think about it like that. That's what we're doing with triple integrals. So we talked so much about double integrals as in we need to now focus our region of integration as being some place in R2, right? So now if we're integrating over 3 variables, that region of integration has itself become some 3-dimensional region actually in R3. So we're taking R3, that's an area that we're integrating over. And so this is where the visualization can become a little bit more tricky. Is when by the time we get to triple integrals, we're no longer really concerned with doing an integral for the sake of like a volume of something. Because like we could do a double integral to find a volume. But then what's past the volume? An integration of a bunch of volumes is going to get you something that's in a dimension we can't really see, external to our field. So what we do instead is we use triple integrals more to start talking about non-physical, so non-directional parameters that are important to consider on 3-dimensional objects. So you could have, imagine if you had certain discs or washers or gears or machinery that's 3-dimensional shapes. In other words, it's taking up some sort of a 3-dimensional region in space. And you might be interested if it's in a car engine, what's the temperature so we don't overheat this thing? Or what's the density of the material that we're doing of this thing? And so if you understand that this function is no longer going to be some spatial, it's not going to be visualized in the sense of, oh, we're making some sort of shadow into 4 dimensions or anything. It's more, okay, this could be, say, the density of my pieces that I'm using that are taking up 3-dimensional spaces. And as I integrate over this volume, I can see, or maybe this is temperature. That's a really, really common one as well. So don't try to visualize this as being, okay, if I have a 3-dimensional region already, where's the integral actually going? The integral is not going anywhere. It's more now we're more interested in summing up parameters that are non-directional about something that exists in R3. And that's going to be the main application. Yes, sir. Yeah, we can do some funny stuff in the pure math perspective. Because then when you start talking about multiple integrations, so then 4 integrals and 7 integrals and 8 integrals and things that are so obnoxious that you really do it, they technically exist. Because all it is you're extending this idea of the Riemannian sum into sequences instead of necessarily this. This is a tuple. So some set of point is a tuple, and tuple, the concept of tuple can be extended to a much more abstract thing that I actually only recently did in topology. And so, yes, there is hardware to extend integration path, but for engineering purposes, this is it. This is the pitch stop. Okay, so good job, you made it. So here is let's recall just a few simple properties. And the reason why they're simple is why I'm bringing them up, because simple means we forget them. The area, so just recall that the area of a region R. So like if we were doing a double integral and we had some region R and R2 that we were integrating over, if we just wanted to find what the area of that region was, we can just assume that the surface we're interested in is the constant 1, right? And so we could say the double integral over R times 1, so then we just have dA. That's the area of R. So then if we're interested in finding a volume, we just extend the idea quite naturally. So extend the idea so that the volume of a region, a three-dimensional region D that we've kind of decided to choose in R3 is just now taking a triple integral over that region, but then of 1, right? We're not doing anything special. We're just going to go dV. Okay, does that make sense? The relationship between what we've already done and now we've taken it up, we've just bumped up one more direction. Okay. So here's a good example of a non-physical kind of dimension situation. So suppose you were testing like steel ball bearings for some sort of a machine. So we have a steel ball bearing. So this is obviously not just a flat circle. So I'll add that for context. So we could describe this as a three-dimensional region sitting in three-dimensional space. So if we give it some context as where it's sitting. And then we're going to call this D. When we're actually doing an integral, what does it mean to do an integral over D, especially if the function isn't just 1? If we chose the function to be just 1, we would be finding the volume of D. In other words, we could find the volume of this particular sphere if we just assumed that the integrand was 1. However, what if we wanted to see how it would handle, say, sitting on really, really hot pavement? So if we have some sort of a temperature function where it's really, really hot on the bottom side of the bearing, but then pretty cool, if we have cooling on the top side of the bearing, we could probably describe that however we want. Is that linear change? Is it exponential change? Is it some sort of polynomial description of decreasing of temperature depending on the variables x, y, and z? Do you see how temperature can then suddenly be some function that would exist even outside of what this region is being affected by? So it's like the temperature here could be something specific. So I could say at x, y, z is equal to 1, 2, 3, it's going to be 55 degrees Fahrenheit. And then if I shift it over, now it's 54 degrees Fahrenheit, or maybe 53. And so we can do similar things. So if you had really hot surface and then a cooling agent on the top of the bearing, that kind of a function could be described with respect to it probably be decreasing linearly with z as you increase, and then depending on where you're at in x and y. We throw that into here. When we take that integral, what we're not saying is we've suddenly gone into the 4th dimension, okay? And then we're finding some sort of other physical object. What we've done is we said the total amount of temperature that this bearing is experiencing at that given moment with that specific kind of temperature surroundings. But it accommodates all 3 dimensions. Yes.
Like, would it be like possible to use the triple integral to see, figure out what area is constantly used for, let's say, like a bearing over time? So like time is what kind of find that where the amount of wear and tear over area.
I see what you're saying. That would probably actually be more applicable to fields, something in surface integrals that we'll do in chapter 17. And so if you're looking at now parameterizing these, and so if you're going to parameterize your spatial dimensions to be changing then with respect to say time. So if this was now moving through space, yes, you could do that. Would I use a triple integral by Riemannian? Probably not, because this is going to be more of a stationary region. and then the function is being applied directly to it. A good question. Okay, so far so good. I'm gonna write out the iterated integral version of what we're gonna be looking at, so. Let me put this here. Okay, theorem. Because it had to be proven. Let f be continuous. Again, we don't want holes or gaps in our regions or surfaces. Over the region. D. And actually, the way we're going to describe D will be very similar to how we've been describing all the other regions, right? We have a collection of points, x, y, z. Okay, so we're specifying this is three-dimensional, and then we're going to restrict x, y, and z between certain things. So this is one such. There are technically 6 different orders of the dv because you have dx, dy, and dz. So there's 6 different or distinct orders of integration. This is just one of the orders, but the others could be applied in a similar fashion. So here is if we're going to do z first and then out to x. So we would have the constant for x here. So a less than equal to x less than equal to b. And then we could say, I'm just gonna continue it over here, sorry. That we could bound y by functions of x, g of x less than equal to y less than equal to h of x. That's actually really similar to what we did with double integrals. And the only thing we're gonna add now is the third variable. So then we're gonna have some g of x, y less than or equal to z less than equal to h of x, y. Where we want to make sure that g, h, big G and big H are continuous. So we don't have any issues there. So then if all those things are true, f is integrable. Integrable, that means we're allowed to actually, it means something to integrate over this region. Integrable over D. And do I have space to put? Yeah, I have space to put. So the triple integral of D for my function f x, y, z, dv can be written as an iterated integral. So as we would iterate with a double integral, so instead of just looking at it generally speaking as the integral over the entire thing, we can split it up sequentially into parts. By doing it in this particular order, we're saying let's integrate with z first, then y next, then x is last. So we'll put the x's on the furthest outside since they're going last. And so we have a to b, then the y's would be next, so little g of x, little h of x. And then the z's are going first, and so that would be big G of x, y, and then big H, x, y. And then we still have our function inside. F of x, y, z, dz. We're going to z's first, then the y's next, and lastly, x. Cool. Questions, comments, concerns?
I have a question. So I was thinking about this before. So with g of x, and then you have big G of x and y, to find z. Can you substitute since z depends on x and y depends on x, can you substitute the x value that y represents in the second set of functions? How does that work?
Right, okay, so this is basically a way to describe breaking down a three-dimensional region.
Mhm.
So this is one case. So this would be used if, say, you had some paraboloid cap up top, but then on the bottom you have another paraboloid cap. So then you already have an explicit explanation of how to get that particular. How can I get from the z's integrated? And then after you do that, you take a look at the top down from just R, and you use your double integral knowledge to look at the projection onto whatever plane to get the others. So that doesn't mean you have to do it in that order though. So suppose you actually had functions x with respect to Z.
Mhm.
You know, and so it's easier to think of the surfaces in that direction. Then you could do the X's first,
Mhm.
and then you look at the remaining plane, which would be YZ, and now that's your new R that you would think about as a double integral.
Okay.
And then you're just relating the functions in whatever's most convenient.
Okay.
So those last two really depend on whatever's convenient that you choose at the start.
Okay.
Yes, so that's why I said this is one of the 6 technical organizations, but since the theory is pretty much all the same, the logic behind it's going to be the same. Yes, good question though. Anything else for this? Yes.
So for B and A integral for the X section, can you technically theoretically plug in B into H of X and then that H of X into the Z? Does that make sense?
Oh, okay, yeah, I see what you're saying.
It's just like numerical values for each integral and each three of them form level.
It doesn't quite work out, and here's the reason why it doesn't quite work out. It's because what this is describing is the special case in which you can describe where you want to start like doing your x's to the end. By the time you get to here, the reason why these are constants, remember when we did the general rectangular regions for a double integral. So it's like where instead of necessarily having nice, clean, constant rectangular stuff, sometimes the way you're restricting a slice can be with respect to functions. So that's what these functions really represent. It's including for the possibility that you have something more exciting than a cube or a rectangular prism. Yeah. So then if it was actually the very first problem we're going to do is just like a rectangular prism. So you can see what would happen if it was just all constants. But then we'll do one where it's surfaces as well. So you'll see what makes. Very good questions. Anything else? Cool. Let's do an example. The irony is I found that rectangular triple integrals were more difficult for my brain to get around than like when we switched coordinate systems. I don't know why, but on Friday we'll talk about, we'll basically do polar, but version 2, because we're just going to add a Z component to polar, and then we'll do spherical, which is really, really fun. And because I think it's fun, that means it's probably going to be on the exam. Sorry. I'm just glad that what I happen to think is fun often coincides with the stuff you're actually going to realistically use in the future, so I have an excuse to indulge myself. But I didn't realize that having a hobby in mathematics was kind of just, it's not just nerdy, it just takes, that's not quite the right word. Maybe obsessive. But
Bigger term.
we need a different term. Well, more like this is what happens when you put homeschooled kid, COVID quarantine, bad math grades, being Asian. No, you put. Yeah, no, it wasn't a good time in high school. It wasn't a good time in high school because I felt entitled to knowledge without practicing. So, now I've learned my lesson the hard way, and now I'm teaching a class of calculus 3 as a 20-year-old in college. It's weird. Life is weird. You know, if you tell God, hey, use me, he will, and it'll be scary sometimes, but it'll always be good. Okay. We're gonna take a solid box D, so start if easy. We're gonna have this bounded by the planes. I would hope they're planes after all the box. X equals 0, x equals 3, y equals 0. Wow, this is nice. Y equals 2, z equals 0, and z equals 1. I look at something like that and I think, wow, it's like giving you the answer for free in the question statement. Because that's going to tell you what A to B, C to D, E to F. This is, and we want to find something else. So the density. So this is a good example of when we're integrating, we're not doing this for a volume or something. We're actually we're taking a 3-dimensional object and then applying a non-directional parameter or dimension, so to speak, density. And then we're gonna see what happens. Density is going to correlate with mass, especially in integration. The density of the box of the box decreases linearly. Decreases linearly. You didn't have to, just for the sake of example. In the positive. Positive. And the direction. And is given by. So here's the description of our density. Density with respect to x, y, and z. So depending on where you're at in three-dimensional space, the density will be given by this rule. It'll be 2 minus z. So if you're sitting on the floor, z equals 0, your density, the box will be dense 2, density 2. And as you're going up, you're actually decreasing how dense this box is. The higher we're going to go up. And so that's not something static. That's something changing. That's something non-physical we can integrate over a region that happens to be a three-dimensional object. And so we can find the mass of the box through integration. So find the mass of the box. Okay, so mass, we're going to sum up all of the density over the region. Our triple integral, region D, f, x, y, z, dv. So to answer Jacques' question, yeah, if it's all constant, it really doesn't matter what order you do this in. Because either way, all the cycles are going to get added up, and there's not being like a problem of intersections. And we can see 0 is less than 3 always, 0 is less than 2 always, 0 is less than 1 always. So I think I put it in here as doing the z's first. And here's where we can choose by convenience. The integrand is going to have z. If the integrand had say x or y, we might change the order. But since the z's coming first, let's just take care of it first. So let's do the z first, and then the y second, then x is last. So x is last. If we're doing that, what's going to be the outermost last? So 0, 3. What's the middle?
0 to 2.
And then if I want to do z's first, what's that going to be?
0 to 1.
Nice. 3, 2, 1. Then 2 minus z is my, don't forget that's the actual thing we're integrating. And then what's the order of the differential is going to be?
Easy dy dx.
I forget people still say v. Z. Yeah, because my handwriting is that bad that if I didn't have a line through that one, you'd be like, the integral of 0 is 0. Okay. So, here's the great thing. You already know how to do that. Just because there's one more step doesn't mean it's just same exact logic over and over and over and over again. So I'll outline the intermediate steps that you should be getting so you can check yourself in self-study. Is that after doing the innermost integral, so if after the z's, we'll end up with integral to 0 to 3, integral 0 to 2, and the result of doing this integral from 0 to 1 of 2 minus z dz is you'll get 3 halves. And then there will be dy here from the outside. So if you do this isolated integral, the innermost integral, if you do that all by itself, you'll end up with 3 halves. And that's going to become the integrand for the next one. And so this is just an integral of a constant. And so this is going to give you 0 to 3, the integral of 3 dx. How do I know that? Just looking at it? Well, because that's just a constant, we can take the constant outside for a second. And all we're doing is we're taking the integral of 0 to 2 of dy. Okay, so that's y. And then we plug in the 0 to 2. So it's literally 2 minus 0 is the way you would evaluate that. 2 minus 0 is 2. That's going to cancel with that 2 and all that stuff. And in a similar line of reasoning, I say, okay, this is just a constant. If I hold it out for a second, I'm just taking integral 0 to 3 of dx. So the antiderivative is just going to be x by itself evaluated on 0 to 3. 3 minus 0 is 3. And then that multiplied by the 3, it should give you 9. So it's the mass of this very specific box that is density is changing with this specific rule. Overall mass is 9. Now, this is linear, so there are probably algebraic methods you could have gotten that, but let's make this exponential and try to get your algebra buddies to do that one. Okay, so this is why we have calculate. You can do these more complicated problems, even though the hardware seems like a bit much. It's like bringing a tank to a knife fight. Sometimes it could make the problem really easy, you know? Okay. This makes sense. So just how this is gonna work, how you set it up, how you actually do it.
Yeah.
Okay, the next one is not gonna be as straightforward, which is why I budgeted about 25 minutes to do it. The reason it's not as straightforward is because there's lots of like little just algebra anecdotes to be made. So it's not that the problem itself is super complicated. Like the concept itself is straightforward, more straightforward than this one, but because the algebra looks a little bit funnier and it involves a little bit more creativity, then it can be perceived as more difficult. I almost didn't do this problem just because my art skills are not 100%, but I will do my best to represent the region that's in this. But sideways paraboloids that are intersecting each other along in separate axes is not necessarily my forte per se. I can barely write the letter S, much less. Okay, so we want to find the volume. Okay, immediately with these three words, you should already know what the integrand is. Which, yes, good. The integrand of this is going to be 1. We'll be taking a triple integral of d over just dv. So find the volume of the solid. D that will be bounded by the paraboloids. And then here they are. Y is equal to x squared plus 3z squared plus 1. And also y is equal to 5 minus 3x squared minus z squared. Okay. So this is realistically what you're gonna have to do with Pearson. Wow, I just slammed. That's good. Nice. Okay.
We're going to the movie boards.
Yep.
I need to give us a whiteboard.
So the very first thing we got to do is we need to visualize what on earth is going on. First of all, how do you take strings of stuff, okay, and then interpret realistically what that's supposed to look like? Because that's probably the question most of you have right now. So here's the idea. If I'm gonna let's simplify the issue. I'm gonna cover up the other variable. What's going on here?
We have a parabola.
With respect to which planes? Okay, so in the xy plane, it's gonna look like a parabola opening upward or downward.
Upward.
Okay, have we done anything to its vertical shift?
Yeah, up
Yes.
one.
Yeah, we bumped it up. Okay, so is this ever going to intersect the, basically, are we gonna intersect 0s at the bottom?
No.
No, okay, so it's gonna be above that plane. All right, what about if I got rid of the x? What are we looking at?
Same thing, but then it's stretched by 3 and then pumped up.
Yeah, so it'll grow a little bit faster, but it's still just an opening up parabola that still has been shifted up by 1. Okay, fair enough. So we're looking at, that's x and z, where y is opening outward. So if I'm gonna draw my reference like this, if I'm gonna have x going this way, and if I'm gonna have y going this way, and z going up, I don't wanna just default to my old habits and make the parabola go like that. Because notice it's not z that's taking the direction of the parabola, it's y that's taking the direction of the parabola, okay? That's the first thing we'll note. And then also, here's the other one, okay? What's the major difference in the signs that are being used here? Yeah, these are both negatives, these are both what? Okay, so you can imagine if we're trying to enclose a region, that should make sense. If you have the opening side of the cups, we should probably close the lid, simple, okay? If I covered up the z's, what do we got going on here?
So curve, it's downward of it.
Yeah.
It goes up, but then it's facing down for a maximum.
We've anchored it higher. Did we anchor it higher than this one?
Yes.
Yes, but is it going down?
Yeah.
So which one? So if I'm moving from the smaller one to the bigger one, is that from here to here over here to here.
Right here.
Left
Left to
to
right, right? Because if I'm anchored at 5 here and opening this direction, if I'm anchored at 1 down here and opening this direction, we're meeting in the middle like this, which means that when I integrate this is going to be the smaller one. That's gonna be the bigger one.
Mhm.
Do you see how this is not algorithmic? I can't teach you every single triple integral problem because the moment they change up the surfaces on me, it's a completely different behavior. So I'm trying to model for you how you can piece this together on your own. These are the questions you ask. These are the clues you look for because you can figure it out that way. All right, and then same thing, that's just gonna be downward. So we have a general idea of what's going on. We're anchoring here at y is equal to what on the left?
1.
Good. And then over here, it's going to be the top what? Good. Now, the one that's going from 1 is opening upwards. So something like, how do I? Got it. Okay, so it's gonna be something like. And then the one that's anchored at 5, is it opening this way or this way? Yeah, this way. I love you just coordinated. Right. So it's gonna be coming down. It's like, oh wait, no, I'm not an egg, I'm a banana, because I'm yellow on the outside, but white on the inside. Man, I gotta stop recording too much. Okay, so the idea is, if I were to take a camera top down from Y onto this, I'm gonna have a shape, right? And because this line of intersection is gonna be projected down onto this XZ plane, right? So here's a region R. Do you see how it's like the shadow? Because we're gonna need to know how to deal with the other variables. The Y's, sure, we might have figured out the order of integration for Y, but we still gotta accommodate how far we're going in the X and the Z direction. Okay, how did I know to do that? Because I just use my brain. There's no algorithm for this. Do you see? I'm trying to. I do. It's very difficult to teach triple integrals over general stuff because there is no longer an algorithm I can just teach you. You just have to know your quadratic surfaces. You just have to know how to do the algebra to get to these circumstances. You have to know how to draw these, and you have to know to get to these circumstances. So this is pretty standard, but it could look different the moment I use cones, maybe, and I'm making a region trapped inside of the cones. Or maybe I took a hyperboloid of 2 sheets, and now I'm trying to trap inside the middle and integrate some sort of elliptical region that I cut out. It's not going to look the same every time, but this is pretty representative of the idea, the thought process behind setting these up. Okay, so here, let's take a look at what's going on. So we know that we're going to be taking a double integral of R. But we know that we're integrating from 1 to, well, like not 1 to 5, you know what I mean, but the left parabola to the right paraboid. So the integral, the left paraboid with this one, x squared plus 3z squared plus 1, and then 5 minus 3x squared minus 2z squared. What's going to be the integrand again? 1. But what's the differential that we're using for the innermost integral here? Good. Why is it dy?
Because the function we're doing is for y equals.
Yes. These are y values essentially. Y equals blah. We're in y equals blah.
So does it matter if we do?
Notice what I've done. I'm trying to show you that fundamentally, triple integrals and double integrals are far more related than you probably think. Triple integrals are double integrals over some sort of a slice. That's all it is. So that's why I'm invoking what you know about an integral of R dA, where the R is this particular shadow, where we're taking care of business right here in between the respective y's. Good. Okay, so let's see. Integrand is 1, so the antiderivative is just going to be y itself. So we're going to do this minus this. So we're going to have the integral, double integral over the R. We're still doing this on the outside, region R. We haven't broken that down yet. But it's going to be the 5 minus 3x squared minus z squared minus the lower bound, x squared plus 3z squared plus 1 EA. Are we all on the same page? Why I'm allowed to just subtract those like that, the top one to the last bottom one? Okay. Yeah, exactly, because it's just 1 to 1. Well, and then we can simplify that. And this simplifies to be the double integral of r with respect, now in the integrand, it's going to be 4 times 1 minus x squared minus z squared dk. Now, if you were just handed this problem originally, you'd think, okay, that's a double integral over a region R. I should probably describe what this region R is. And if you take a look here, what shape? Is this a nice rectangle or is this more rounded out? Okay, so which tools do we use for rounded out things? Yeah, polar is probably gonna be easier, unless you really want to find the translation equations with square root. So let's describe R. I'm gonna make a new picture here. And we have a circle. Well, actually, we don't really know what that is. I'll do a step. We talked about, yes, I'm projecting this down. If I were to shine a light exactly down Y, what would its shadow be on XZ plane? Well, the way we find that is basically this intersection. So we need to know the intersection of these two paraboloids to know what the description is in X and Z. Does that make sense? So I'm going to set my two paraboloids equal to each other because that's going to tell me the relationship between X and Z in the shadow. Okay, that's a fairly typical strategy here. So so the one on the left is X squared plus 3Z squared plus 1. And then the other paraboloid is 5 minus 3x squared minus z squared. Do we know what we're doing here? Or why we're putting these things equal to each other?
You're looking for the intersection?
Yes, we're looking for the intersection because that's where they're going to be the same. We're looking for where they're the same. Now, if we simplify this, I'm going to kick this over. I'm going to kick this over. I'm going to have 1 plus the 3 is 4x squareds. 3 plus the 1 is 4z squareds. And then if I kick this over, 5 minus 1 is what?
4.
Okay. Well, we have a redundant constant 4, so let's simplify that. We have x squared plus z squared equals 1. That should be immediately recognizable as what shape?
Circle.
Good. With respect to which axes, though?
X.
Yeah, axes then. So now it's a little different. So if I'm looking at that top-down view, I've essentially got that region R that's hooked up like this. And now I'm gonna change so this will be Z here, this will be X here, and this is the region R. This is a unit circle. Now, if we're going to be integrating in polar, because that's going to be far easier, we can describe R using polar coordinates. So what are the two variables for polar coordinates in a double?
R theta.
Theta. And then what are we bounding the radius? What are we sweeping out? Yeah. So I'm basically starting in the center, and how far am I going out? 1.
To 1.
I sweep out 0 to what?
1.
Start at 0, sweep out to what?
1.
0, sweep out to what?
1.
Okay, and then if I keep going, how many radians am I doing this around for?
2, 5.
5. Okay, so when I create the inequalities here, what am I going to put for R?
0
3, 5.
Want and just theta be 0 less equal to theta less equal to 5.
Beautiful. Does that make sense to everybody?
Yes.
Okay, so now we have that set. The only thing we haven't really fixed is our integrand, right? Because our integrand is still in these Cartesian coordinates. But if we multiply, well, so more like if we're thinking about circles in X, Z, I'll put a little thing over here. So this is what's going on in your very intelligent brain all the time. You say X squared plus Z squared is equal to the radius of a circle squared, right? And so this is minus and minus, so minus X squared minus Z squared is equal to minus R squared. So we really have one minus R squared to convert. So we have what's going to be on the outside when you convert to polar.
4.
Yeah, theta is going to be 0 to pi. And then after the theta, what's going to be the next limits of integration? 0 to 1. Still have the 4 chilling. 1 minus R squared, because that's what that is. In polar, what is dA? In polar coordinates, what is dA?
Theta.
And if you have it to be in polar coordinates, what is dA? Good. So do you see the difference? We plugged this in, but then we added another part. Here's an instance where I'd actually say it's faster to not distribute this in, because you've been given a U substitution for free. You could just say that U is, that's the most terrible U I think that you've done. Here's U equals 1 minus R squared, and so then du is just minus 2RD. But we already have 4, so I would just need to change this to minus 2. And then when I do the switcheroo here, because it'll be 1 minus 0 squared is 1, 1 minus 1 squared is 0, it will be 1 to 0. That doesn't make any sense. You flip it around, you hit another negative sign, so you'll get back to positive in your integrand. So this is going to get you to 0 to 2 pi. It gets flipped back around to 0 to 1, because before it was 1 to 0 directly after the U sub, but directly after the U sub it was negative, so we just flipped it back to be 2U to U d theta. Okay. Did that make sense?
Kind of.
Okay. What can I explain better?
When it comes to changing
The limits.
bounds on the inner integral, could you just leave it as an indefinite integral, solve it, and then once you convert it back from U to R, then you put the bounds of 1 and 2?
You could, however, in multiple integrations, that's a lot of extra hanging garbage you don't really want to forget about. So it's best to keep it clean per layer of integration.
Okay, so in this case, how do you just stay, it stayed as 1 and 0 because you was.
Oh, I'm realizing what's confusing now. Okay, here, let me erase. Actually, no, I can just keep this. Okay, so what's happening is when I do the. We need the definition of U, I just realized that, so U equals 1x R squared. So what happens is we have the integral from 0 to 2 pi.
Yep.
And then if I do the U sub, this is technically R is equal to 0.
Yep.
Well, I need to adjust that to U world. So if I plug 0 into here, I get 1 minus 0 squared. What's that?
1.
Okay, so now we transform that to a 1.
Mhm.
Now 1 minus 1 squared is what?
0.
So then R equals 1 gets transformed to 0 in U world.
Oh.
Now the du is minus 2r dr, but I already have a 4 over here. So I need negative 2 times u du d theta. Because the du is minus 2r dr.
Sure.
And if I multiply that by minus 2, I get back to positive 4 times this. So that keeps this constant.
And so multiplying the integral by -1.
To get this flipped back around is 0 to 1.
That makes, okay, now I understand.
Yeah.
Thank you.
Is that good enough for everyone? So
Yes.
this is what was this was the intermediate kind of reasoning between that. So then this isn't too bad, because that's just u squared. Man, I almost budgeted my board correctly. I'll put it right here, so it'd be 0 to 2 pi. And then we're evaluating u squared on 0 to 1. So what's 1 squared minus 0 squared?
One.
Yeah, so this should be just d theta, which is 2 pi, because the antiderivative is 1, so 2 pi minus 0. That's pretty cool. So the volume of this, we've been trapped 2 pi volume inside of some paraboloids. And that is a very pretty wave function. Very pretty. Okay, questions about anything involving this problem?
Wait, explain again, you said the 4 divided 2, that 4?
So the 4 already has, think of the 4 as minus 2 times minus 2.
Yeah.
The reason why we don't think about this, because we need to borrow minus 2 for the substitution. So RDR is actually negative 1/2.
Oh.
Yeah, so then we had to make sure we accommodate for that when we multiply it.
Oh, okay. Then it is minus 2 here.
You mentioned, go ahead, six different ways in which you can get a mirror. Is there a method you've learned for each pattern?
No, so if it's in Cartesian, the order that you're gonna use is gonna be entirely dictated by the surface, the region that you bounded. So in this case, we were bounding y with respect to x's and z's. Who's to say that we could have done the same problem analogously, but x is now the paraboloids are with respect to y's and z's. So naturally, you're gonna change the order of your Cartesian integral, but it's not necessarily like a rule that you memorize. I'm saying the only thing that will become specific is on Friday when we talk about cylindrical and spherical. Those are the only two systems in which you say, no, we actually want to do it exactly in this order. And you'll memorize it in the order that you'll always integrate. But this, yeah, no, it's free game. That's why it's a little bit more difficult. It's because then you have to choose for yourself what you want to interpret, and then the algebra you're willing to do essentially for the problem. Because there's probably another way to do this. But this is easier.
So is it that if there's a negative, you just switch the limits, like you switch them around?
Yeah, so there's a property with definite integrals where if I hit minus, then I can change the order of my limits of integration. That's a fun little thing. So if I like randomly hit, let me see where I can put that property. So if I did negative the integral from b to a of some f of x dx, then this actually just switches it back to regular a to b of x.
Okay.
Yeah. So that's what's going on here, is I'm saying, okay, I have a negative 1 to 0, so if I just got rid of the negative sign, then I can put it back to regular order. Okay. Scale of 1 to 10, how are we feeling about this?
6.5.
It'll feel a whole lot better when you do one on your own in the Pearson. It'll start, the pieces will start clicking. Okay, there's one more definition you need to know, but it's analogous to other stuff we've done, so it won't take that long. Right. Good to erase?
Mhm.
I almost don't want to say goodbye to that, it's so pretty. Yeah, it's pretty, okay.
Definition.
Mhm.
Definition, average value a function f over a region D. Actually, I'm gonna let you should know what this is, just by nature of doing the average value of f over r. So let's see. Colby, what's the definition gonna be for average value now that we're talking about 3 dimension?
For the integral,
Well, average value of a function over a 3 dimensional region D.
uh. the one over- There'd be three intervals now would be. Iterates be.
Let me give you a hint. Think back to the average value when we did it with just a double integral. Yes, Diego.
Would be the, one over C minus B minus A to the term.
I think you're overcomplicating this accidentally.
One over the volume,
Yes, say it louder for everybody.
one over the volume,
Yes, because the volume of this region, volume of D, then the triple integral of D. Okay. And very good. Because the average value when we were doing double integrals was 1 over the area of R. So it's whatever the unit, whatever the region's dictating how the average works here. Because in Calc 1, it's just 1 over B minus A, which is the length of your interval. And then in 2 dimensions, it's area of your region, 3 dimensions, volume of your region. Yeah. Cool, yo. Cool. Well, you guys have an exam today, so I'll let you guys go earlier than usual. Well, not by much, like 6 minutes. Best of luck to you all. I will see you on Friday, for last round of triple integral stuff.
That's already clear.